So today we'll continue our discussion of mincost flow, and hopefully we'll get towards the first primal dual algorithm that we will see in this course. So recall that in mincost flow, you have every vertex has a demand that is referred to as BV, and we'll say if BV is negative, then it is a source, and if BV is positive, then it's a sink. But we can switch these around. We will look at transshipment problems where all capacities are infinite, and we're going to minimize the cost of the flow. So we already have a pre-specified demand that needs to be satisfied, and we need to minimize the cost of the flow. And as we described last time, a min-cost flow problem can be reduced to transshipment in linear time. Min-cost flows with negative weights are very general and cover lots of different problems. So given a min-cost flow or a transshipment instance, the first question to ask is, is it feasible? And the second is, does an optimum exist? So recall that we can split all the vertices technically into three categories: sources, sinks, and those that are neither. So we have the total supply, which is whatever needs to be sent from the sources, the total demand, which is whatever needs to be sent to the sinks. And what we argued is that a min-cost flow is feasible if and only if we can construct a max flow instance. And if the max flow instance has a max flow which is exactly the total supply or the total demand, then the min-cost flow problem is feasible, which means that actually there is a flow exists that can route these demands. And we also, using max flow min cut, we had a particular description. We had an alternate characterization in terms of sets of vertices, the cut, and their demand. We will come back to this lemma later on, maybe in the next lecture or so. But what the upshot of this is that we can determine if a min-cost flow instance is feasible by running a max flow problem. So that solves the feasibility question. Now suppose the min-cost flow, and in this case we'll just think of a transshipment instance as feasible with some flow. So you construct some flow X which satisfies all the demands. Then the way that you update the flow is by a circulation. You basically send flow along a directed circuit, which means that it doesn't affect any of the flow conservation constraints. A circulation is a flow where the flow coming in is equal to the flow coming out. So you can always add a circulation to any existing flow without affecting the flow conservation constraints. And because in this case the capacities are infinite, there are no capacity constraints, but certain edges may not exist, so their capacities would be zero. So we can update flow along a circulation. So this is just to give you a sense of how you would do some augmenting. And before we get there to the actual augmentation, I wrote this theorem, and we need to prove this, which is if the transshipment LP is feasible, meaning that suppose there exists a flow, then an optimum exists if and only if G has no negative cost die circuit, meaning there is no negative cost circuit. And we drew a simple example here where when you have a negative cost cycle, then there actually is no optimum, right? Because the optimum is essentially it's like minus infinity. You can keep adding circulations to this negative cost die circuit and repeatedly reduce the cost. And as we discussed, we can always find a negative cost circuit using Bellman-Ford. So we can determine feasibility by a max flow, and we can determine if an optimum exists by Bellman-Ford. So this is where we are. I'll take any questions you have about the setting before I go into the proof. Any questions about this stage? Anything that any doubts that you have about mincost flow, this is a good time to ask, because we will be launching into the proof and sort of more complex algorithms for mincost flow. All right, it seems that there are no questions, so I will proceed with the proof of this theorem, actually, and all right, so here's the first question. How can we prove that an optimum exists? Using the dual. Any thoughts? How would you use the dual to prove that an optimum exists? Any suggestions? All right, so here's a question. Suppose the optimum exists. Or let me step back. The LP is feasible. The transshipment problem is feasible. Let's recall what the dual problem is. Remember, the dual is this problem, which is to maximize the sum of BV YV, which is some weighted combination of YVs, where YVs basically satisfy like a shortest path type condition. So this is referred to as a potential. There's a variable for every vertex, and it has to satisfy something that looks like a shortest path condition on the prices or the costs, and the costs may be negative. So that's a potential. That is a potential. First question. Suppose there is a negative cost die circuit. So let me actually just start by writing the easy condition, which is just look at the contrapositive. If G has a negative cost die circuit C, we can add circulation to C to reduce cost. So the optimum does not exist. So the LP is feasible. There is a feasible solution, but it's essentially unbounded. And so I'll just say exercise to finish the details. But there's not much more to write. Just leave it as an exercise to finish the details. So if there's a negative cost die circuit, we can add a circulation to this die circuit, this directed circuit, and we can reduce the cost. And so you can keep doing this and keep reducing the optimum. What does this tell you about the dual? What does this tell you about the dual? Let me put the dual up in front. Remember, there's the dual there.
Are you trying to ask, or shall we say something like the dual will be unbounded?
Okay, good. So good. So yes, exactly. I'm trying to understand what is it about the dual that you can say when there is a negative cost die circuit. When there's a negative cost cycle, what can you say about the dual? Let me rephrase this question. If you have a graph with negative cost cycles, can you define shortest path distances? Yes, no?
So you can't find the shortest path because the cost will be negative, and then you just can't use the normal shortest path algorithm to find the shortest path.
It's even worse. When a negative cost cycle exists, shortest paths cannot be defined.
Yes, because they can go looping the negative.
They can keep looping, which means that you can never satisfy these equations. You can never satisfy these equations if there is a negative. Okay, I think this is. I'd like to go slowly here because what we're doing here is really fundamental, and this is the core of understanding primal dual algorithms, which is a very deep concept in algorithms. So I want to make sure that we go slow and all of you understand what's going on. These equations define shortest path distances. Okay? Now let me draw a little picture. Let me draw a little picture over here. Suppose there's a negative cost cycle. Okay? So what does this mean? So I'll just call this V1, V2 up to Vk. So what do I know? I know that the summation, and for convenience, I'll just say Vi is equal to Vk plus 1. I'll just call them the same thing. So I is equal to 1 to k. The summation of the price from Vi to Vi plus 1 is less than 0. That's what a negative cost cycle means. Now suppose for all edges uv yv was less than yu plus the price. Now let's plug this in over here and we'll see what happens. Let's sum this from I equals 1 to k y of vi. Right, so I'm just going to apply this for vi plus 1, I equals 1 to k y vi plus summation I equals 1 to k p vi to vi plus 1. So I've simply summed up the conditions over all of these, right? I've summed up V2, I'm just saying YV2 is at most YV1 plus the price of V1, V2, so on and so forth. What does this lead to? These actually cancel each other out. Which is strictly less than 0. This is a contradiction. Okay, so what does this mean? What does this mean? I got a contradiction here. So what can you say about the dual? What can you say about the dual? When there is a negative...
Feasible.
I'm sorry?
It's not feasible.
It's infeasible, exactly. Exactly. So the dual is infeasible. And this is an if and only if. So let me say what I mean by if the optimum, if the dual is infeasible, then the optimum does not exist. And if the optimum does not exist, then the dual is infeasible. Let me write this out. So this is a very fundamental point. So here's the primal. And we're saying the primal is feasible. Right? Because that's what we're saying. We're saying the LP is feasible. So you take the dual. Now by strong duality, the optimal value of the primal is equal to the optimal value of the dual. And recall that right now the way that the primal is some kind of min, right? So it's a min of summation over E of CE. The price of E times the X of E, and the dual was a max summation over V of BV YV. Now we know that the dual is feasible, and we're seeing if there is a minimum. Just by weak duality, we know that for all feasible dual solutions, for all feasible dual points, and for all feasible primal points, and I say point instead of solution because solution is really the optimum, we know that the dual objective is at most the primal objective. Right? Okay. So now can someone guess how do you prove that the primal has no optimum? Or how do you prove that the primal does have an optimum? Looking at these. Looking at weak duality.
If you can say the dual objective is not infinity.
If you can say the dual objective is not infinity, if you produce a specific primal point, can the dual objective ever be infinity? Suppose I just gave you the dual objective of the point. So let's just say there's for all feasible dual points y, for all primal points, the dual objective of y is at most the primal objective of x. Suppose I showed you some y, which was feasible for the dual. Suppose I showed you a feasible point for the dual. Then can the primal objective be minus infinity? So what you're saying is that you need to show that the dual objective is not minus infinity, but I'm just saying that suppose I produce a feasible dual point, any feasible dual point. That dual point is going to have some finite objective value because it's just some finite, it has some specific values. And the moment the dual is feasible, then the primal objective is lower bounded, which means the minimum I mean, I guess technically the infimum exists, but then the minimum will also exist. Does this make sense here? So let me write this out. So the primal has an optimum if and only if the dual is feasible. Which is a very nice way of trying to characterize whether an optimum exists or not. Just prove that the dual is feasible. Showing feasibility is much easier than proving that something has an optimum or does not have an optimum. Because for feasibility, you just have to produce a point. And if the dual is not feasible, so if the primal has an optimum, then the dual has to be feasible, basically by strong duality. We know the opt of the primal is the opt of the dual. But if the primal does not have an optimum, then the dual is infeasible. And that's because if the dual was feasible, then by weak duality, we actually have a lower bound on the objective value of the primal. Does this make sense? Any questions at this point? This is a very fundamental aspect of duality and one of the use cases of duality. Questions? I'm happy to take it slow today and answer any questions that you have. Okay. So, this brings us to, we proved the forward direction. To prove the negative direction, we just need to show that if G has no negative dicircuit, then the dual is feasible. And if the dual is feasible, then an optimum exists. And why is it easier, I should say, to prove that the dual exists? When we look at the dual, forget the objective. We just need to show the dual is feasible. All we need to do is produce distance labels. We just need to produce a distance function, a shortest path distance function. And intuitively, if G has no negative cost dicircuit, then we know that a distance function exists because you can run Bellman-Ford. So you can run Bellman-Ford, and in any graph which does not have a negative cost circuit, negative cost cycle, we know that shortest path distances exist, and the shortest path distances give us the dual solution. I will write this out more formally, but any questions about this idea? Okay. So now let me write out the proof of the other direction. So we're saying that suppose G has no negative cost directed circuit. Okay. So here is G. We'll just create a new dummy vertex S and have all costs PSV P0. Okay, so it's going to have an edge from every S to every V. I said dummy vertex S, edges SV, and all these costs are just 0. These prices are just 0. Now, because G has no negative cost dicircuit, shortest path distances from S are defined, and this is really, technically this is, I suppose a theorem of Bellman or Ford, but you could just use Bellman-Ford to find these. So for every V, define or set YV to be the shortest path distance. Shortest path distance from S. And this vector YV is dual feasible. Hence, the primal objective is lower bounded. Lower bounded, optimum exists. Is lower bounded and primal is feasible. Primal is feasible, hence the optimum exists. Okay. Questions? Does that make sense? Continue. Okay, good. So what we have proven is that the optimum exists if and only if G has no negative cost die circuit. So now in polynomial time we can determine if a transshipment problem and hence a min-cost flow problem is feasible and an optimum exists. Now let's discuss augmentations. Now let's discuss augmentations in or for min-cost flow. And when I say min-cost flow, in this context I usually mean transshipment problems. So given a flow X, let us define the residual graph G of X. Okay, so it's similar as before, except we also now need to add costs. Okay, so let X UV be strictly greater than 0. So this is some edge with the flow. So what we do is we have the forward edge from U to V. We already had this edge before. So the price of this edge is PUV, and its capacity is of course infinite, right? Because if you route more flow, you know the capacity will remain infinite. We add a negative edge where the price is now minus PUV, because this was already routing flow. So essentially if you reduce flow, you get to reduce the cost. This was now going to have a capacity, and the capacity is going to be exactly XUV. Right? This is going to have, this edge will have a capacity. And so this defines the residual network. Right? This gives the residual graph G of X. Does this make sense? The price is going to be negative, because by routing flow from V to U, this is in effect reducing flow from U to V. So you reduce the cost, but there is a capacity now. So even though you started with a transshipment flow, when you do the residual graphs, you will have capacities. The reason why I used transshipment problems is just that the dual then becomes a lot more simpler. Okay. Now let me prove another theorem which is of interest. Suppose X is feasible, right? So we have a feasible flow, and G of X has no negative cost die circuit. Remember, G of X is different from G. So G, even though G has no negative cost die circuit, G of X may have a negative cost die circuit because we introduced all these edges. Right? We introduced these extra edges. So G of X may have a negative cost die circuit. It is absolutely possible that G of X may have a negative cost die circuit even though G does not. But what we'll say is that suppose X is feasible and suppose G of X has no negative cost die circuit. This is equivalent to X is optimal. So I should say suppose X is feasible. Then G of X has no negative cost die circuit if and only if X is optimal. So previously we had a condition of feasibility, the existence of an optimum. Now we actually show how to prove that there is an optimum. Okay, and so clearly the backward direction is easy. And so if G of X has a negative cost die circuit, we can add a circulation and reduce total cost. Hence, X is not optimal. Let's look at the forward direction, and we use the same idea as before. Suppose G of X has no negative cost die circuit. Okay, so we'll do the same construction. Add dummy S as before and define YV as before. So remember for V, YV is the shortest path distance to S. Now observe the following. For all edges UV, this is an edge in the residual graph, right? Because the residual graph has these. For all edges UV, we have Y of V is at most Y of U plus P prime of UV, where P prime of UV is the cost in G of X. The costs in G of X may be different from the costs in G. So we're saying if UV is an edge in G, then YV is at most YU plus PUV. But if VU is edge in G and UV is like a backward edge, then yu is at most yv plus puv. Right? Okay, now observe the following. Suppose xuv was greater than 0. Then g of x has edges uv and vu. Hence, yu, yv, if you put these together, what you get is that yv is equal to yu plus puv. Remember, if it's a backward edge, the reason why u and v are reversed is because p prime uv is negative. If g has edges uv and vu, then yv is equal to yu plus puv. Now what? This dual constraint has become an equality. So can someone tell me what the next step is? What is this condition called? Yes? Any thoughts? What is this condition called? Everything is related to duality in some way, right? So here's a primal solution, here's a dual solution. Anyone want to hazard? 2 words that I'm looking for. Yes?
Complementary slackness.
Complementary slackness, exactly. So this satisfies complementary slackness. So x and y satisfy complementary slackness. X is primal feasible. And y is dual feasible. And y is dual feasible because shortest path distance. It's a shortest path. So what do we know? If x and y satisfy complementary slackness, x is primal feasible and y is dual feasible, what can we conclude? That x and y are optima. And that ends the proof. So now we have proven that x is an optimum. So what we're saying is, if G has no negative cost die-circuit, and you compute the shortest paths, using this Bellman-Ford, then actually what you get is complementary slackness conditions hold, and therefore it must be optimal. X is primal feasible, Y is dual feasible, and if you can find any X and Y that are each primal and dual feasible such that they satisfy complementary slackness, then X and Y are optimal. So X is optimal. And that proves that if X is feasible and G of X has no negative cost die-circuit, then X is optimal. And this gives us the first primal algorithm for min-cost flow. I mean, this works for min-cost flow in general, but I've been discussing it in terms of transshipment problems, which is what's called the primal augmenting cycle algorithm. Is initialize X to any feasible flow. I'll just say that if G has a negative cost die-circuit, then just reject. And because we know no optimum exists. And then the main step is we'll say, while G of X has a negative cost die-circuit C, then we can just augment a circulation in C to reduce cost, and then just update X. And I will, so each augmentation, this is a run of Bellman-Ford. So unlike max flow, where each operation was just BFS or DFS, here each augmentation requires a Bellman-Ford. And you can prove a theorem, and this is fairly straightforward given everything that we've done so far, given all of the things that we've done so far, that assume all all demands are integral. So when you assume they're all integral, then every time there's an augmentation, then you augment at least one unit of flow. So if you assume all the demands are integral, then a min-cost flow, or I should say the transshipment flow, can be computed in O of Mn times. So Mn is what you get for each min-cost, for each Bellman-Ford times U, where I should say, or rather, U is an absolute value of the optimal cost. So this is not a polynomial time algorithm, right? And this is behaving exactly like this was given by Ford and Fulkerson, and this is basically the Ford-Fulkerson procedure. Any questions about this? Okay. So now that we know that we have some algorithm, we're going to build on these ideas. I'm going to give you the primal dual algorithm, which is also not going to be a polynomial time algorithm, but then we'll show how to improve upon this algorithm to give a polynomial time algorithm. So this algorithm is called a primal algorithm because we always maintain a feasible primal point, which is the flow. The primal dual algorithm will, interestingly enough, it maintains an infeasible primal point X and a feasible dual point Y, such that complementary slackness holds. So it's kind of interesting. Instead of actually trying to increase the objective or decrease the objective, whichever way you look at it, instead of trying to improve the objective, it's actually going to maintain a feasible dual point and an infeasible primal point such that complementary slackness holds. And then it is going to reduce the infeasibility in each iteration and update X and Y. So the important point to notice is that the complementary slackness conditions will always hold. So when X is finally feasible, it is automatically optimal. So it's automatically optimal. Okay. So let me now describe what is the X that we're going to maintain. The X is going to be a flow. The X will be a flow that does not satisfy all demands. So it's what we can think of as a partial flow. Whereas in the primal algorithm, we initialize to a feasible flow. So a feasible flow is something that has satisfied all the demands. Here we're going to route only a partial flow. And this is going to look like Ford Fulkerson, where you route a flow and then you keep trying to route more and more flow. But it's more complicated because you now also have to worry about the cost of every flow that is being sent. So the way to think of this is, so let's try to think of it as follows, that some vertices still have supply demand left. So in G of X, we have sources and sinks. So let's say that here is G of X. Again, recall that in the primal algorithm, G of X doesn't have any sources or sinks. And that's because it's a feasible flow. So all the demands and supplies have been taken care of. The only updates are by circulations. In the primal dual algorithm, the situation is much more complicated. G of X is going to have some sources and sinks. So there are going to be some sources here and some sinks here. I'll call them S sub X, T sub X, because these are the sources and sinks in the residual graph. And now what we need to do is, so we have G sub X, so we have some X that does not satisfy all the demands. And we're going to have, we have some dual feasible Y such that complementary slackness holds. Such that complementary slackness holds. We will try to route flow from Sx to Tx, maintaining complementary slackness. So let's step back a second. What is complementary slackness? Again, so we have x and we have y, and so for all edges uv, we know that yv is at most yu plus puv. And what we have is if xe is not equal to 0, then yv is equal to yu plus puv. Now it is going to be convenient for me to define the following. So what I will use is I will use p hat to denote the cost in g of x, right, in the residual. So remember that the cost in the residual, for a forward edge the cost is the same, but for a backward edge the cost is the negation, right? So the cost is the negation. So p hat denotes the cost in g of x. And I will say that y is dual feasible with respect to g of x if for all uv in g of x, yv is at most yu plus p hat uv. Okay? So now let me state, it's a fairly simple claim, but one that is very important for us. In g of x, if y is dual feasible, so if y is dual feasible, or maybe I should just say, if y is dual feasible with respect to g of x, then x and y satisfy complementary slackness. The proof, which I'm going to leave as an exercise, but I'm going to show you how the proof is done, because I already did this in one of the previous calculations here. Is remember we did this calculation that said that if uv is an edge and uv is a backward edge, then the difference between these conditions give equality. So remember we said that if g of x has edges uv and vu, then yv is equal to yu plus puv. So if you have any y that is dual feasible with respect to both of these edges, then actually you have equality, and that equality is exactly the complementary slackness. So the proof is an exercise. But what is important to note is if I can maintain the dual feasibility with respect to g of x, then x and y will satisfy complementary slackness. So this is going to be the overall picture then. Here is g of x, and here are the sources of x and the sinks of x. I need to route flow, because if I route flow, then I can reduce the overall demand and supply that has not been satisfied. I need to route flow and update the y to satisfy. I need to update the y, so route the flow and satisfy, update the y to satisfy dual conditions, dual with respect to the new g of x. Right, because we have a y value at every vertex. Okay, so ignoring this for now, we know that in g of x, y satisfies the dual constraints. This is sort of by assumption. We're assuming that we start from that point. After routing flow, where does the problem arise? So what happens? Why is it when you route flow? Can someone tell me where does y stop being dual feasible? Like, what is the problem? So let me pause here. So this is exactly what I want to get at, right? When you route flow, let's try to understand where things break. Because instead of me sort of marching through the proof, marching through the discussion, I think it's important to understand where things are going to fail. So if uv and vu exist in g of x, then yv is equal to yu plus puv, not just p hat, but puv, because that means complementary slackness holds. Right, and that's because I said that if y is dual feasible with respect to g of x, it satisfies complementary slackness. Let's just say that you have y that satisfies, let's say y is dual feasible with respect to g of x, complementary slackness holds. So if you decide to route more flow along this path, complementary slackness will still hold. Does that make sense? Complementary slackness simply means that whenever there is an edge through which flow is going, then this condition needs to hold. So what is the problem? So I think whatever was suggested, you're almost there. So what is the problem now? So why is it that when you route flow, complementary slackness will fail? Let me maybe rephrase it differently. Suppose you have this other path here, and it has these edges. And maybe this back edge exists, and that back edge exists. But this is only by itself. What can you say about E in this case? So question, is XE 0 or non-zero? Is XE, suppose you just have a single edge. Is XE 0 or non-zero? Raise your hand if you think it's 0. And I guess maybe clap your hands if you think it's non-zero. So maybe just use the reactions. So raise your hand if you think it's 0 and clap your hands if you think it's non-zero. Why would it be non-zero if there was a forward edge in x? This is before you route. Before you route. G of x has not done the augmentation. So if G of x looks like this, then is there flow going, then is XE 0 or non-zero? So it is 0, it's actually 0. Because if it was non-zero, there would be a backward edge. So if only the forward edge exists, then the flow is 0, right? Otherwise, the residual would have put a backward edge. Is this clear? So please stop and ask me, because most people thought it was the opposite. So let me make sure I clarify this point. In the residual graph, if there is no backward edge, then that edge could not have been carrying flow in g of x, or in x. Is that clear? So xe is 0. And after the augmentation or the routing, or I should say maybe augment. After the augmentation, xe becomes non-zero. So there is an edge through which no flow was going, and then you decide to route some flow. Now you have a problem, because complementary slackness means, let's say that this was uv, yu plus puv. But before the augmentation, you only had an inequality. There was no complementary slackness here. So complementary slackness does not imply anything here. If xe is 0, then complementary slackness gives you nothing. So there's no slackness constraint. When a primal variable is 0. When a primal variable is non-zero, then you have a constraint. So something needs to change. Does this make sense? So please feel free to ask me questions here. I want to make sure that all of this is clear. Like, you understand the intuition behind this, because once you understand the intuition, the proofs are going to be a lot easier to read. Does this intuition make sense? So when an edge that was previously zero, so no flow was going through this, then you decide to route some flow here. Now you have a problem, because now there's an additional complementary slackness constraint that needs to be maintained, which was not being maintained previously. If the edge was already carrying flow, then you don't have a problem, because it was already carrying flow. You already maintained complementary slackness there. So you already had this equality condition. So if you route more flow, it's not a problem. The problem is when you route flow through an edge for the very first time, then the slackness constraint is problematic. So, raise your hand if things make sense right now. Raise your hand if things make sense. Okay, I only see one hand going up, so the rest of you should ask me questions then. So there's something in the chat, although it is harder for me to read the chat. It says not everything, but would like to sit and read. No, go ahead and ask me questions at this point, so that what is the point that is maybe the most unclear? What is the point that is the most unclear? And then I can clarify. I'm happy to sort of clarify, because while discussing, I can probably answer a lot more questions quickly than if you were to try to figure some of this stuff out yourself. So what's the point of confusion? Like, where is it that you're getting sort of stuck? Is it the overall picture, or? So let me step back and sort of say what is going on here. There is some partial flow. You are trying to route more and more flow. So the x is the partial flow. You will maintain a current dual solution given by the y's. Maintain complementary slackness. Now, this claim says if you can maintain the dual feasibility with respect to g of x, then you will satisfy complementary slackness. Another way to put this is just to say that if both uv and vu exist in g of x, then yv is equal to yu plus puv. This is really what this claim is saying. So you can forget about the claim and maybe just think of it this way. And this is the same thing as saying that complementary slackness now holds for that edge. Or this, because for that edge, if uv and vu exist in g of x, that means that the flow there is non-zero. Now suppose there's an edge where the flow is 0, so no flow is being routed. If you decide to route flow using an augmenting path, then you're going to have to satisfy complementary slackness with respect to this edge E, which was not being maintained before. You didn't have to maintain any constraint for that edge. And so the dual variables have to change. So what I'm going to describe now is a high-level description of a simpler primal dual algorithm. I'm not going to analyze all of it. I just want to put it out there and make sure that you understand. And then in the next lecture, I can do sort of a more advanced primal dual algorithm, because I don't want to throw out the more advanced version until the simpler version is clear, but I don't want to do the analysis of the simpler version because it's really not that substantial. So here's the idea. We'll call an edge an equality edge if, so the edge is uv, if yv is equal to yu plus puv. So call this edge an equality edge. It's a directed edge, remember, it's u to v. So if this condition holds. Right, this is again with respect to the original graph, if you have this equality condition hold. So if there is a path of equality edges from a source to a sink. This is sources and sinks in g of x. So again, you can just imagine putting down an edge wherever this constraint holds. Yv is equal to yu plus puv. And if there is a path of equality edges from some source to some sink that just takes equality edges, then route flow along that path. Right, so this is safe. You can always route flow along this path because complementary slackness will hold, because you've already maintained the slackness constraints. Right, so if there is a path of equality edges from a source to a sink, you can route flow along that path. And complementary slackness holds. So when do you get stuck? When do you get stuck? Yes? It's just reversing this condition. So when do you get stuck? It means that
when you can't find the augmenting path along that.
You can't find a path of equality edges. Exactly, right? If you can find a path where all the edges satisfy this equality condition, then you can always route flow along that and not worry about complementary slackness. Where do you get stuck is exactly, yes, the situation that I showed before, but it's that there is no path of equality edges from a source to a sink. What this means is that inequality edges form a cut between sources and sinks. I'll phrase this alternately. I'll say let me give this a name. I'll say U be the set of all vertices, so I'll call this all U, such that there is a path. I'll call this an equality path. Right? There's an equality path from a source to U. So here's your graph. Here are the current sources S of x. Here's T of x. And so there's something in here. This is U. These are all the edge vertices that can be reached by an equality path. By an equality path. So what do you know about all of these edges? What do we know about all of these edges? These are necessarily inequality edges, right? So if you have any, and let me use A and B, then we know that YB is strictly less than YA plus BAB. So for all of these edges, right, for all AB, and note that these edges form a cut. They're separating sort of the sources from the sinks. So now how do you make progress? Now how do you make progress? What can you do to the dual now? So you know that for all edges, YA is strictly less, YB is strictly less than YA plus PAB for all edges that are going from this side to this side. So what you can do now is you can actually increase all the dual variables in U, right? Because everything in U, I'm sorry, not increase. Well, you can increase these or decrease the other. Let's go ahead. Let me see if I. Yes, I'm sorry. Let me do it in V minus U. So I can increase the dual variables for everything on the other side. I can increase the dual variables. Right? Because YB is strictly less than YA. So I can increase it by a little bit and still maintain the constraint. And so if I increase the dual variable for everything in here, I can maintain all the constraints in here by the same amount, same, I'll say small amount. So if I increase the dual variables for everything, this constraint over here is maintained, right? Because I'm just looking at the difference in these constraints. And each of these constraints will be maintained because each of them was a strict inequality. I can always increase everything by something small. If any of them was an equality, then I'd get stuck. But the whole point is they're not all equalities. So I can increase all the dual variables by some small amount. So you increase all the dual variables, and then recompute U. And you kind of keep doing this process, where actually I should say go all the way here. If the inequality edges form a cut, you find U, you increase all the dual variables, recompute, because, or rather, U will increase. So as you increase all the variables on this side, one of these edges is going to become an equality. One of these will eventually become an equality. It's strictly less than, eventually it becomes an equality, then U will now contain that as well. And you keep doing this until you get a path from a source to a sink of equality edges. Then you go ahead and route flow. And then you keep repeating this procedure. So this is a basic primal dual algorithm. This is the basic primal dual algorithm. So we have about 10 minutes. We have two options. So one is I can continue a bit, or I'm happy to actually end the lecture here and just take any questions that you have about mincost flow up to this point. I can answer anything anywhere. And I'll let you go ahead and choose, and I can maybe even look at the chat if it comes to that. So, raise your hand if you would like me to stop and to take questions. Okay, and clap your hands if you actually want me to continue and do more. Okay, so since most people did not vote, and there was only one vote for me ending the lecture, I will go ahead and end the lecture now, and I'll take any questions you have in the remaining time.